slides?
Yes, we can see them.
Okay, perfect. So thank you for the introduction, and I'm lucky to be here. I'm very happy to be here. And today I'm going to show you how we can use the gamma ray emission from stars to probe the density of cosmic rays throughout the galaxy. And stars emit thermal radiation. So how can they emit gamma rays? And what happens here is that the gamma rays that we are willing to observe from stars, they are not coming from the stars themselves, but from the inverse Compton scattering of cosmic ray electrons in the thermal photons surrounding the stars, in the photon halo of the stars. And from Fermi-LAT observations of the sun, we know that the gamma ray emission from stars, they may come in two main steric components, which are the disk component, the stellar disk, and the stellar halo component. And from the disk, the emission is expected to come from cosmic ray cascades generated in the atmosphere of the star. And this process is not that well modeled even today. But from the photon halo surrounding the star, the extended emission is expected to come from the inverse Compton scattering by cosmic ray electrons. And this process is way better modeled than the disk emission. So what you can see here in this plot on the left is that we have the disk emission in pink for the sun, and the halo, the photon halo gamma ray emission in green. So the blue line is the sum of both. And you can see that the gamma ray emission from the sun can extend beyond 10 degrees from the center of the sun. So the sun is huge in the sky in gamma rays. So we can use, this is the point of this work. We use the gamma ray emission from stars to constrain the density of cosmic rays, of cosmic ray electrons actually, throughout the galaxy. This equation here on the left is the intensity of gamma rays, and it depends on the emissivity that depends on the density of photons surrounding the stars and on the cosmic ray electron spectrum. This parameter here, the density of photons, it's well known for several stars, because if we have the distance of the star measured correctly, then we can very precisely predict compute the photon density around the star. So we are left with the cosmic ray electron spectrum. You see in the next slides that we built some models for these stars in gamma rays, and for these models we had to assume a cosmic ray electron spectrum similar to the one that we use here in the solar system. But this may not be the case. So if the cosmic ray electron spectrum is way higher at some point of the galaxy, these stars can emit more gamma rays. So the luminosity of a star in gamma rays, it depends on the optical luminosity of the star multiplied by the radius from the star. So if you integrate from the center of the star and go to increasing radius in the photon halo, then of course you have more inverse Compton scattered gamma ray photons. So the luminosity increases. And this makes the flux depend only on D. D is the distance from the Earth to the star. So it's not D squared, it's only D, the dependence of the flux, the total gamma ray flux. And we can see here that the energy density of photons surrounding superluminous stars like O-type or B-type stars, they can be way above the average interstellar radiation field energy density, up to more than 10 parsecs from the star. So this tells us that from the point of view of a telescope like the Fermi-LAT, these sources should appear as extended sources in the sky. Although the luminosity drops, the flux drops really quickly from the center of the source, like I showed you here. Okay, we selected a sample based on this that I just told you. We selected a sample of 9 nearby superluminous stars that were expected to be on the edge of the Fermi-LAT sensitivity. So these are the 70 very bright and nearby stars. So we are selecting only those with predicted fluxes, with the highest predicted fluxes. So here, just for giving you some idea, this circle, red and green circles, represent the Kappa Orionis, Zeta Pulpis, and Zeta Orionis stars. And we are willing to detect them with Fermi-LAT. So each one of these stars, these 9 stars, was modeled with an extended map constructed with this software here called Stellarics. And gamma rays from each star, as I told you, give us this precise information about the cosmic ray electrons in the surroundings of each star. For this model here, the cosmic ray electrons cannot penetrate deeper than 0.025 degrees. So this dot in the middle, it's a bit darker than it should be if there was not this limitation here. So we are modeling the stars as extended sources, but also as point-like. So we are using these 2 types of models. And this is, I basically told you already this. And we can use these stars to map the density of cosmic ray electrons. And the more luminous is the star, the better it is, because it will emit more gamma rays, so it's easier to be spotted by gamma ray telescopes. And of course, that a non-variable star is preferred, because in this way we know better the density of thermal photons surrounding the star. We have a steady source of thermal photons. So we found no significant gamma ray emission from coming from these stars, and these are the gamma ray spectra for 2 of them, but we have more 7, of course. And in blue and orange, we have the inverse Compton emission models integrated within 1 degree from the center of the star and 8 degrees from the center of the star. And in red and black, we have the upper limits for the point-like model that we compare with the blue line, and for the extended model that we compare with the orange line. So for lots of these upper limits, we are relatively close to the predictions. So we are not more than we are less than 10 times higher than the predictions. So since we didn't detect each source individually, we tried to detect the stars as a population. So we stacked the Fermi-LAT data that was coming from all of these 9 stars and tried to extract a signal from the population as a whole. However, the population is not, the population, everyone together is not emitting a significant amount of gamma rays. And in this plot here, we have the square of the significance in the y-axis and the photon index of the star that we have to assume this to make the stacking. And we found that the blue curve is the curve corresponding to the targets, and the black curve is the curve corresponding to mock stars that we randomly scattered in the regions of interest. So we see that the significance of the targets is basically the same as the significance of the background. So we found no signal in the end. However, we can still constrain the density of cosmic ray electrons in the surroundings of these stars. From what we found, we put an upper limit in the flux of the population, where the average gamma ray emission for each star has to be less than 3 times 10 to minus 11 photons per centimeter square per second. This in the energy range from 500 MeV up to 100 gigaelectron volts. And if the flux was higher than that, we should detect the population at least at a 3 sigma level. And this measurement also constrains the density of cosmic ray electrons in the surroundings of these stars. If the density was higher than twice that observed here in the solar system, then we should detect the population at the 3 sigma level. And to detect it at the 5 sigma level, the density of cosmic rays should be 4 times higher than what we have here in the solar system. So this is basically what this plot is saying. So in the y-axis, we have the significance. And in the x-axis, we have actually the flux of the population, what it should be in terms of what it is. So to detect it at the 3 sigma level, the population should be at least twice brighter, 2 times brighter. And at the 5 sigma, it should be more than 4 times brighter. This here predicted according to our models created with Stellarics. And that's it. This is the summary of this work. So we can use stars to investigate the density of cosmic rays, of cosmic ray electrons in every point of the galaxy where we have a sufficiently bright star in gamma rays. The Fermi-LAT has insufficient sensitivity to detect these stars, even if they are superluminous and nearby. We could not find a significant gamma ray signal in the stacked analysis, but we could put an upper limit, which already give us some useful information. And we constrained the cosmic ray electrons, electron density to be less than twice that observed in the solar system at the 3 sigma level. You are all invited to read the paper, and that's it.